Hello everyone. In this video, we're going to talk about parametrizations for circles and for circular movement, as well as parametrizations for portions of graphs of functions that you studied in algebra. What's this computer doing? Okay, here we go. To start with circles, let's begin with an exploration. And let's suppose that we're dealing with a vector valued function that has a couple of unknown constants in the formula. We have a constant called r and a constant called omega. And the only thing that we know for sure is that these are positive numbers. Let's try and figure out what those numbers represent and what effect they have on the graph of this vector valued function. Okay, first let's attempt to sketch the graph of this vector valued function. And I'm going to start by plugging in a couple of different times and figuring out the corresponding positions. Now, if I plug in r equals 0, if I plug in t equals 0, then regardless of the value of omega, cosine will become cosine of 0, which is equal to 1, and in the back I will get sine of 0, which is equal to 0. So at time 0, our location will be r units out along the positive x-axis. Now, if I tried to plug in t equals 1, a next sort of natural time, then it would be impossible for me to answer exactly where is this object located at this time because I don't know the value of this constant called omega. Instead, let's try and plug in slightly different values of t so that I will be able to figure out the corresponding locations. For example, what if I considered where I was when t was equal to pi over 4 divided by omega? If I plug in that time, then the two omegas would cancel each other out, the divided one in my time and the multiplied one in the formula. And it would simplify to simply pi over 4 radians. And so that would be located in the upper right corner of the unit circle. Root 2 over 2, root 2 over 2, each one multiplied by this number r. So that would be up here, r units away from the origin at time pi over 4 divided by omega. Now, by a similar reasoning, if I plugged in pi over 2 divided by omega, then that would correspond to the position at the top of the circle, 0, r, and so on and so forth. And it would trace out, in the counterclockwise direction, a circle of radius r. So that answers our first question. How does the quantity r affect a graph? This is the radius of the circle. But more interesting perhaps is the question, how does this mysterious quantity called omega affect the graph that's formed? To answer that question, I'm going to think about what it would take to loop all the way around this circle and return to the right side. Now, under normal circumstances, one full loop around the circle would be achieved when the angle was 2 pi. But this time, let's take that 2 pi and divide out by omega to compensate for the multiplied omega that is in the formula. The multiplied omega and the divided omega cancel each other out. And so I'm left with cosine and sine of 2 pi, which will put us back on the right side of the circle. So we'll complete one full loop. So what is the significance of the quantity called omega? Well, one significance that we can deduce is that the object will complete one full loop in a time interval of 2 pi over omega. At time t equals 0, it was on the right side, and then if I plugged in time 2 pi over omega, then it was back on that right side of the circle. So this represented the amount of time that it takes an object moving along this function to complete one full loop and return to where it started. In other words, in the language of trigonometry, the so-called period of this movement is 2 pi over omega. Okay, now what if I change the game slightly, and instead of having positive omega inside of sine and cosine, I had negative omega inside of sine and cosine? Well, once again, if I tested this by plugging in a couple of sample values of t, then you can confirm at time t equals 0, we're once again on the right side of a circle of radius r. But this time, if I try and move forward in time, for example, to pi over 2 times omega, let's see what happens if I plug that value into this vector valued function. If I clean that up, then I'm left with cosine of negative 2 pi, which is 0, and sine of negative pi over 2, which is negative 1. So now, as I have moved time forward, I have ended up traveling to the bottom of the circle. If I continue with those calculations, plugging in various values of t, I find that exactly the same circle is formed. A circle of radius r equals whatever. One loop completed in 2 pi over omega units of time. But the big difference between the example in the previous problem, where we had a plus omega inside sine and cosine, and this problem where we have a negative of omega inside sine and cosine, is the orientation of the curve. If you have a positive scalar inside sine and cos, then you will be traveling counterclockwise. But if you have a negative number, then you will be traveling clockwise, essentially backward. Once again, though, the radius of the circle is r. The period of the circle is 2 pi over omega. The big difference is the orientation. So bearing in mind what we have observed, let's try and find vector-valued functions that represent the movement described in the following examples. Suppose we have an object traveling in a circle with a radius of 50. So I'm going to make a note of that. We want a radius of 50. So extrapolating from our previous examples, we want our value of capital R, this number multiplying on the outside, to be equal to 50 units. We want to move in the counterclockwise direction. So I know, based on our previous experiments, that if I want to move counterclockwise as opposed to clockwise, then my sine and cosine are going to have a positive number on the inside, omega times t. Now we know that one lap is completed in 20 seconds. The time it takes to complete the lap is the period. So we want the period of the movement to be 20 seconds, and therefore we want 2 pi over omega to be equal to 20, because we found that 2 pi over omega was the amount of time necessary to complete one lap. Now from this, we can deduce that omega is equal to pi over 10 units, rearranging and simplifying. And from this, we have all the data that we need to parameterize the circular movement described in this example. The radius is 50, the x is cosine, the omega is pi over 10t, and I'm going to leave it positive because it needs to be counterclockwise. For y, the radius is 50, we use sine, omega is pi over 10t, and I'm going to leave it positive because we want this to be counterclockwise. So this would be the vector valued function representing the movement. For a slight remix, suppose we have an object that's traveling in a circle, radius is still 50, but the next little change is this time that we're moving in the clockwise direction. We also get something interesting. We are no longer given the amount of time it takes to complete one loop around the circle. Rather, we're given the object's speed. So let's try and figure out what the value of omega would have to be so that we can fill in the blanks of that general circle template formula. So for a circle of radius 50 meters, working on finding omega, the circumference of this circle, in other words, the meters in one lap, can be found by taking 2 times pi times the radius. So if this is the number of meters in one lap, and the object's speed is 30 meters per second, the seconds that is required to complete one lap the period, in other words, 2 pi over omega, in other words, must be equal to the distance required divided by the speed at which we're traveling, 100 pi divided by 30. So cleaning that up ever so slightly and solving this for omega, we get that 6 pi divided by 10 pi must be equal to omega's value. And cleaning that up yet further, find that omega must be 3/5. Okay, so now we found the radius, we found the value of omega, and we've noted that our object must be traveling clockwise. To parameterize a circular movement with those properties, we can now use the following. Our R value is 50. For x, we have cosine. The omega value that we found is 3/5, and I'm going to make that negative because we're traversing the circle in the clockwise direction. Then we have r equals 50. For y, we use sine. Once again, a negative because of clockwise, and then our omega, and then our t. So, in summary, the formulas given above, r cosine, sine, and r cosine sine with negative inputs, are what we use to parameterize circular motion. The value of capital R is equal to the radius of the circle. We use the period of the motion, the amount of time to complete one loop, to calculate the value of omega. And then we either do not or do include a minus sign in the input, depending on the orientation of our movement. The last curve that we will parameterize in our work is the parametrization of a portion of a function, like we studied in algebra. So for example, let's parameterize the curve formed by graphing the function y equals 3x squared plus 5. So what I would like to do is I would like to find a formula, x of t for my x component and y of t for my y component, so that the following property is satisfied. I need the y of my parameterization to satisfy the same equation as the abstract y that I am given in this function. Y of t has to be the same thing as 3x of t squared plus 5. That is necessary so that every point on the graph of the parameterized curve is on the graph of the function. The outputs of my parametrized curve, the x and y components, will satisfy the equation, which means that that will be a location that's on the graph. Now here's one choice, and generally speaking, the simplest and most reliable choice. The simplest choice is to just replace x by the simplest varying quantity, let x be equal to t itself. And then, what must y be equal to match? It must be equal to 3t squared plus 5. Now that is not the only possible choice here, not by any means. If you wanted to, for example, another choice would be to set x of t equal to something else, like 1 minus t, for example, and then y of t would have to compensate to match that. Y of t would have to be 3 times that x squared plus 5 in order to satisfy the given equation. But in my experience, there's not really much reason to go with the more complicated choices like this. In my experience, you can usually go with this nice simple choice, this one here, where the independent variable is just replaced by t, and then the other variable moves to match that. For a related example, suppose at this time that we had x as a function of y. X must be equal to sine of y. In this particular case, the only thing that really needs to be true is that the x of my parameterization and the y of my parameterization satisfy the same equation as the x and y given to me in this problem. So there's one very simple choice once again. Let me just let the independent variable be replaced by t. And then let's make x move to match that. No longer sine of y, but now sine of t. That's the approach that I would use to parameterize graphs of regular algebra functions. I would replace the independent variable by t, and then I would cause the dependent variable to match that.